There is a machine that most people have seen hundreds of times and never really looked at. It sits on construction sites, beside roads, at the edge of building projects. When it works, the arm swings out, the bucket drops, and a load of earth that would take a person hours to shift disappears in seconds. When idle, it just sits there, enormous and unremarkable. Most people walk past and think, that thing is a brute, built for punishment, the kind of machine where a few millimeters here or there cannot possibly matter. That thought is wrong, and it changes how you see every construction site you have ever passed. An excavator is one of the more precisely manufactured machines in any industry, and the gap between what it looks like and what it takes to build it is larger than almost anyone would guess. Let's get into it right here on Small Things. Not just a digger. The operator sitting in that cab is managing 4 separate systems at once. The steel structure carries the load. The hydraulic system converts fluid pressure into the force that moves the arm. The electrical system reads sensors and manages controls. The mechanical joints allow the machine to swing 360 degrees and hold position under load. Each system only works if the others were built correctly. A hydraulic system delivers full pressure only if the joints it acts through are properly aligned. The swing bearing only lasts its intended life if it was seated within fractions of a millimeter. The operator pressing a lever and watching the arm respond is the visible end of a long chain that started with a weld measured under a robotic scanner. Why robots replaced human hands. Imagine 2 welders on the same factory floor, working the same shift, welding the same joint on 2 different machines. The experienced one has 30 years of muscle memory behind every movement. The newer one has 2. Both joints look fine to the eye, both pass inspection, but one has fractionally less penetration, fractionally more internal stress. Neither welder knows which one. That machine goes to a job site. It starts its dig cycles. After 2 years, one joint begins to crack, not at the surface where anyone would see it, but from the inside where the stress concentrated. By the time the crack reaches somewhere visible, it has been growing for months and has already propagated into the surrounding steel. This is what variation does, and it is why the industry changed. Engineers calculate how long a structure will last based on assumed weld quality. If the welds are consistent, the calculation is reliable. If the welds vary, some machines fail earlier than predicted, and because the failure starts inside the metal, there is usually no warning. So the welding robots arrived, not because they are faster, though they are, but because they are the same every time. The 1,000th weld is identical to the first. Same heat, same travel speed, same penetration, same stress profile. The structural joints that carry the full force of digging are identical across every machine on the line. And when every joint is identical, the engineers who calculate fatigue life can trust their numbers. The machine will last as long as the calculation says, because the weld it was calculated for is the weld that was made. The inspection robots followed for the same reason. A human inspector catches obvious failures. They cannot measure the geometry of every weld to the millimeter accuracy that determines whether it will hold. A robotic scanning system maps every joint on every frame, compares the measurement to the specification, and flags anything outside it before the frame ever reaches the assembly line. Not approximately, exactly. Human welders did not disappear from these factories. Their role shifted to setup, calibration, and the irregular work robots still cannot do. But the thousands of repetitive structural welds that determine whether a machine holds together in the field became the robot's job. The machine that buries itself in rock for a decade has to be the same machine on day 3000 as it was on day 1. From steel to first start, raw steel arrives at the factory as separate components. the pieces of the boom arm, the sections of the upper frame that will house the cab and engine, the track frame that will carry the machine's weight on the ground. None of these can carry load yet. They need to be joined, and the joining has to be strong enough to survive repeated cycles of stress that would fracture a weaker connection in months. Robotic welding fuses the pieces together at temperatures exceeding 1,200 degrees Celsius. The heat does more than join metal. It also introduces stress into the surrounding material as it cools. Controlled welding procedure, correct travel speed, correct filler material, correct heat input ensures the stress is distributed in a way the joint can carry. An incorrect weld introduces stress concentrations that can crack under load invisibly from the inside. After welding, robotic inspection systems map every joint against the engineering specification. Color-coded imaging shows variation across the surface. Anything within specification is flagged green. Anything outside is flagged before it ever reaches the assembly line. The frames are then coated. Paint on an excavator is not cosmetic. Bare steel corrodes, and corrosion weakens structural integrity progressively through years of exposure to water, soil, and temperature extremes. While frames are being built, the components that make the machine move are assembled separately. The travel motors, which drive the tracks, are bolted to the sprockets that engage them. The swing bearing, the massive ring that allows the upper body to rotate on the lower, is installed with precision tooling. Then the two halves of the machine are brought together. The upper frame, carrying the cab, engine, hydraulic pumps, wiring, and hoses, is lowered onto the lower frame and bolted through the swing bearing. For the first time, the excavator exists as a single unit. Then comes the first startup. Before the machine can move, every hydraulic line must be bled of air. Hydraulic fluid is incompressible and transmits pressure instantly. Air is compressible and absorbs pressure instead of transmitting it, causing sluggish response and component damage. The machine cycles its cylinders repeatedly until every air pocket is cleared. The roughest machine has the tightest tolerances. Standing next to an excavator on a job site, watching it tear into compacted ground and swing a full bucket across the frame, it is easy to assume that somewhere in that machine the tolerances must be rough. Something this violent in its work is probably forgiving of a millimeter here or there. It is not. The swing bearing, the ring that allows the upper body to rotate on the lower, is seated within fractions of a millimeter. Not because excavators are delicate, but because of what happens when it is off. A bearing seated even slightly off-center distributes load unevenly around its circumference. Under thousands of dig cycles, that unevenness grinds one arc of the bearing while the rest sits idle. A bearing engineered to last years begins to fail in months. By the time the failure is visible on the surface, it has already traveled into the surrounding structure. The cylinder pins, at the joints where the arm segments rotate, are sized to allow smooth movement with no play at all. A pin with even small looseness impacts the housing every time direction changes. Over tens of thousands of cycles, that repeated shock creates fatigue cracks, not immediately. Quietly from the inside, building until the joint fails. This is the pattern across every critical joint on the machine. The rougher the work, the tighter the tolerance has to be, because the forces are so large that even a small imperfection becomes a large failure very quickly. Where precision meets the real world, a finished excavator rolls off the line and onto a truck. From there, it might go to a city block where workers are cutting the foundation for an apartment building. The trench has to be dug to a specified depth and alignment because the structural engineer calculated the footing placement on that assumption. If the machine's reach is off, the trench is off, and the foundation is wrong before a single pour of concrete happens. The precision built into the factory follows the machine all the way to the ground, or it goes to a mine, where it will run 24 hours a day, completing tens of thousands of dig cycles every year. A bearing seated correctly at the factory will last its engineered life. A bearing seated at the outer edge of tolerance will degrade faster than calculated, in a place where a breakdown means idle equipment, idle crews, and lost production counted by the hour, or it goes somewhere no test anticipated. After a flood, after a building collapses, an excavator is often the first machine on the rubble. The loads shift without warning. The ground gives way. The machine runs for days without a service stop. In those moments, no one is diagnosing a bearing that was slightly off at the factory. They are relying on the machine to keep working, and the machine either does or it does not. The ones that do are the ones where every joint was built correctly the first time before anyone knew where the machine was going. Brute force, hidden precision. Go back to that excavator sitting idle at the roadside. Before it ever got there, robots welded its frame in a sealed enclosure too bright to look at directly. Other robots scanned every joint for variation too small for a human eye to find. The two halves of the machine were lowered together and bolted through a bearing seated to fractions of a millimeter. The engine fired for the first time, and the machine spent hours bleeding air from every hydraulic line before it was allowed to move. Then it went to a construction site and started tearing into the ground, and nobody watching knew any of that had happened. That is the hidden story of the excavator. Not the power, which is obvious, the precision that makes the power reliable, which is invisible until it fails. If this changed the way you look at the next excavator you pass, let us know in the comments what you want us to explore next. We might make it our next episode. Thanks for watching. History often hides in the smallest details.